Professor Belfrost's computer science class is back!
Hi, welcome back. And here's Professor Belfrost's class on computer science. And today we are going to explore another concept on computer science, continue our last lesson. And if we are already ready for today's episode, then let's go. Well, great for us. Thanks for joining the class again. So now let me explain about instruction formats. Okay, so as the use of an instruction format. So an instruction format defines the layout of the bits of an instruction in terms of its constituent fields. So an instruction format must include an opcode and implicitly or explicitly zero or more operands. And its explicit operand is referenced using one of the addressing modes that have been described before. So this is the important note about this session. So there are some important points here related to instruction formats. Let me explain one by one. The first one is instruction length. So yeah, the instruction format length, and it will affect and is affected by the memory size, memory organization, bus structure, processor complexity, and processor speed. And this decision determines the richness and flexibility of machine, as seen by the assembly language programming. Okay, the most obvious trade-off here is between desire for powerful instruction, repertoire, and need to save space. Okay, so we as programmer always want more opcodes, more operands, more addressing modes, and greater address range. Because it will make our life to be easier and shorter programs can be written to accomplish a certain task. Okay, and it will give us a greater flexibility in implementing certain functions. But of course, it will make us okay need to increase the main memory size and also increasing the use of virtual memory. Okay, and this is the trade-off that has been explained before. And also beyond this basic trade-off, there are other consideration as well. So either the instruction length should be equal to the memory transfer length, or one should be multiple of the others. And also, you need to see that here this rate has a keep up with increase in processor speed. And also, memory can become a bottleneck if the processor can execute instruction faster than it can fetch them. And a seemingly mundane but nevertheless important feature is that the instruction length, so the multiple of the character length, which is usually 8 bits, and of the length of fixed point numbers. And yeah, we again see this word, which is word okay itself. So word length of memory is in some sense the natural unit of an organization. And the size of a word usually determines the size of a fixed point number. So yeah, that's the important thing to notice here. Next one is allocation of bits. So yeah, for a given instruction length, there is a clear trade-off between the number of opcodes and the power of addressing capability. Okay, so as can be seen that um, for an instruction format of a given length, this reduces the number of bits available for addressing. And there is one interesting refinement to this trade-off, and it is by using variable length opcodes. Okay, so there's a minimal opcode length, but for some opcodes, the additional operations may be specified by using additional bits in the instruction. And for fixed length instruction, this leaves fewer bits of addressing. Okay, so this will require fewer operands and or less powerful addressing. And here are some interrelated factors that will go into determining the use of the addressing bits. We have some, okay, register versus memory, number of register sets, address range, and address granularity. Okay, so here are some example that maybe I will skip it because we're not being involved in it. We're not going to depth. Okay, let's go directly to variable length instructions. Okay, so here's the important thing. But the designer may choose instead to provide a variety of instruction formats of different lengths, which will make it easy to provide a large repertoire of opcodes with different opcode lengths. And addressing thus can be more flexible with various combinations of register and memory references plus addressing modes. Okay, and the principal price to pay for this variable length instruction is an increase in the complexity of the processor. Okay, and the use of variable length instruction doesn't remove the desirability of making all the instruction length integrally related to the word length, because the processor doesn't know the length of the next instruction to fetch. Then a typical strategy is to fetch a number of byte a word equal to at least the longest possible instruction. Okay, here we also have some example. Okay, to follow up, TDP11, VAX. I will skip it for now. Okay, and then we'll see a little about x86 and ARM instruction formats. Let's see if there's something here. This is quite machine specific. Maybe I will skip it. Okay, let's see a little about assembly language. Though I will teach you later about assembly, but let's see later. Let's see it prior. Just a quick view. So a processor can understand and execute machine instructions. Such instructions are simply binary numbers stored in the computer. And if a programmer wishes to program that in machine language, it will necessary to enter the program as a binary data. So this is a weakness. We must program it with binary data. Do you understand binary data? 1 and 0s written together as a string and what it means? Yeah, maybe most of us don't. So what we can do is, okay, the first improvement is to write the program in hexadecimal rather than binary. This is the first improvement. But this is also not convenient. So for more improvement, we can make use of a symbolic name or mnemonic of each instruction, and this is called symbolic program, as shown in the figure. Okay, so this is symbolic. This is binary program, improved to be hexadecimal program, and later improved again to be symbolic program. And you see, if it is a memory referencing instruction, the third field contains the address to store and relay data and location, we invent a pseudo instruction with the symbol dot. This is dot. Okay, this is the highlight of the symbolic program. But later, maybe when we face more complex program, then this is kind of still awkward. And then we are introduced with the last refine, which has to deal with assembly language. So program written in assembly language are translated in machine language by an assembler. And yeah, this is kind of assembly language, but later maybe I will show you some kind of programming in assembly language, but maybe not now. Okay, so we're done with this chapter. Let's see the next chapter. Processor structure and function. This is very vital. Okay, let's see how much I can cover today. Oops. So a processor includes both use of visible register and control status registers, and the former may be referenced implicitly or explicitly in machine instruction, and user visible register may be general purpose or maybe also have a special use, and yeah, it depends, such as fixed point or floating point numbers, traces and indexes, and segment pointers. Control and status registers are used to control the operation of the processor. Okay. Later we'll see this term PSW that contains a variety of status and condition bits. Also, processor makes of instruction pipelining is good to speed up executions. The pipelining involves breaking up an instruction cycle into a number of separate stages that occur in sequence, such as fetch instruction, decode instruction, determine the operand addresses, fetch operands, execute instruction, and write operand instruction. We'll see it later, okay? So yeah, here's the first point. We begin with a summary of processor organization. Register which form the internal memory of the processor are then analyzed, and we'll discuss the instruction cycle. Okay, so this is the outline how this chapter will be brought to us. Yeah, so first, processor organization. Fetch instruction. The processor reads an instruction from memory. The interpret instruction. The instruction is decoded to determine what action is required. Fetch data. The execution of an instruction which may require reading data from memory or an I/O module. Process data. Okay, which is some AL. Okay, I mean arithmetic logical operation. Writing data. Okay, to a memory or an I/O module. And to do this thing, it should be clear that processor needs to store some data temporarily, and this is small internal memory. Okay, this is when we make use of small internal memory. Okay. Okay, so you see here, the reader will recall that the major components of the processor are ALU and CU. The ALU does the actual computation of processor data, while the control unit controls the movement of data and instruction into and out of the processor and controls the operation of the ALU. And in addition, that we have minimal internal memory consists of a set of storage location called registers. So here's, yeah, we may have seen this picture before, right, in the previous lessons, but yeah, here we made this figure one again. So yeah, the data transfer and logic control are indicated here. So we have control bus, data bus, address bus. Okay, and this is called internal processor bus. Okay, this is needed to transfer data between the various registers and ALU because the ALU is in fact operates only on data in the internal processor memory. Okay, so you can see here's internal CPU bus. It interacts with registers and control unit. We also have a complementary shifter, status flags, arithmetic and Boolean logic inside the arithmetic and logic unit box. Okay. So let's see how a register actually organized. So actually there are two roles that performed by any register in the processor. Okay, the first one is user visible registers, which enable the machine or assembly language programmer to minimize main memory reference by optimizing use of registers. Then we have control and status registers that used by a control unit to control the operation of the processor and by privileged operating system programs to control the execution of programs. Okay, let's see some category of user visible register. We have general purpose one, data, address, condition, codes. First, general purpose. So general purpose registers can be assigned to a variety of functions by the programmer. Okay, sometimes they're used within the instruction set is orthogonal to operation. That is, it means any general purpose register can contain the operand for any opcode. But there is restriction. For example, there may be dedicated register for floating point and stack operation. But in some cases too, it can be used for addressing function. And in some other cases, there is a partial or clean separation between the data register and address register. Okay, so for data register, it may only be used for hold data and cannot be employed in the calculation of operand address. Oops. And for address register, they may themselves be somewhat general purpose or they may be devoted to particular addressing modes. Okay, let's see some of the example. This is very important, okay? I want you to memorize these terms because maybe we will need this words, terms later, and this is kind of important. The first thing is segment pointers. So it is used for segmented addressing. The segment register hold the address of the base of the element. Okay. Then for index register, they use for index addressing. For stack pointer, yeah, it's very clear. Okay, is a dedicated register that points to the top of the stack. Okay, and there are several design issues. The most important one is to whether use a completely general purpose register or to specialize the use. Okay, with the use of special register, that it can be generally be implicit in the opcode which type of a register a certain operand specifier refers to. And the operand specifier must only identify one of set of specialized register rather than one out of all register, thus saving bits. But the other hand is that the specialization limits the programmer flexibility. So there is a trade-off between flexibility and identification. Okay. Another design issue is the number of registers, either general purpose or data, plus address to be provided. Okay, so number of register is the second thing or is the second issue. Okay. And also there's issue about the register length. Okay, that registers that must hold addresses of user must be at least long enough to hold the largest address, and they should be able to hold values of most data types. Okay, we are done with most register, but there's a final category which is called which is at least partially visible to the user, holds condition codes or flags. That condition codes are bit set by processor hardware as the result of operation. Okay. And you see condition codes bits are collected into one or more register, and usually they form part of a control register. Okay, so this is important thing. And here is the advantages and disadvantages in using condition codes. Okay, here's the summary. Then we are discussing about the control and status register. Okay, so there are four registers, the essential to instruction execution, as shown here. We have PC, IR, MAR, MDR. For PC contains the address of instruction to be fetched, IR contains the instruction most recently fetched, MAR contains the address of a location in memory, MDR contains a word of data to be written to memory or the word most recently read. But not all processors have internal registers designated as MAR and MDR, but some equivalent buffer mechanism is needed, whereby the bits to be transferred to the system bus are staged and the bits to be read from the data bus are temporarily stored. Also, this is important point. Okay, let's see. Here is the process. Okay, so typically the processor updates the PC after its instruction fetch so that the PC always points to the next instruction to be executed. Then a branch or skip instruction will modify the content of the PC. The fetch instruction is loaded into an IR where the opcode and the operand specifiers are then analyzed and then data are exchanged with the memory using the MAR and MDR. And at a bus organized system that the MAR will connect directly through the address bus and the memory buffer register MBR will connect directly to the data bus. And user physical registers will in turn exchange data with the MBR. the next paragraph and go into the second after paragraph. So yeah, we have some kind of register or set of registers. It's called PSW, Program Status Word, that contains status information. Okay, so PSW typically contains condition codes plus other status information. And here are some common fields or flags that is in the PSW. We have sign, we have zero, we have carry, we have equal, we have overflow, we have interrupt enable or disable, we have supervisor. The number of other registers related to the status and control can be found in a particular processor. Okay. Okay, there may be a pointer to block of memory containing additional status information. Also, maybe we have a interrupt factor register for a machine that uses the factor interrupt. Or if a stack is used, then we have a system stack pointer. And there are still many kind of these things that we will later encounter. And here's the example of microprocessor register organization. You see that is quite complex. Okay, so we have data registers here from D0 to D7. We also have address register here from A0 to A7. We have program status, program counter, status register. The general register includes accumulator, base, count, and data. Pointers or index. We have stack pointer, base pointer, source index, destination index. Segment, we have code, data, stack, and what is this? Extra segment. Okay. And then we have flex instruction pointer, yeah, and we have some others. Now we will dive a little into what called a instruction cycle, and this will be the last topic on this lesson. Okay. So instruction cycle includes the following stages, but let's first see from the figure. Okay. We have interrupt, fetch, indirect, execute. Let's see. So this is the instruction cycle actually. For fetch, it's actually a terminology which means write the next instruction from memory into the processor. Execute means interpret the opcode and perform the indicated operation. For interrupt, okay, if it is enable, then an interrupt will occur. It will save the current process state, and the service will be interrupted. Okay. So let's see. We have indirect cycle. Okay. So as we have discussed before, the execution of an instruction may involve one or more operands in memory, each of which requires a memory access. Okay, then if indirect address is used, then additional memory accesses are required. Then the main line of activity consists of alternating instruction fetch and instruction execution activities. So after an instruction is fetched, then it will be examined to determine if any indirect addressing is involved. If so, then required operands are fetched using indirect addressing. And following the execution, then interrupt may be processed before the next instruction fetch. Okay. And once the instruction is fetched, then the operand specifier must be identified, and each input operand in memory is then fetched, and this process may require indirect addressing. Okay. But register-based operand needn't be fetched. Okay. And once the opcode is executed, the assembly process may be needed to store the result in main memory. The next one, I think this is the last one. Let's see if I'm correct. Oh, okay. I think there's still some. Okay, just finish up till this data flow. So the exact sequence of events during instruction cycle actually depends on the design of the processor. Okay, let's see. Let's assume that a processor that we buy in person MER, they also have MBR, APC, and IR. So here's what happened. During the fetch cycle, the instruction is read from memory, and the PC contains the address of the next instruction to be fetched. Then it is moved to the MAR and placed on the address bus. Okay? Please pay attention to this figure. Okay, this figure is a complete picture from all the explanation that will be given. Okay, also this. Okay, we have data flow, the fetch cycle. It's all happening inside the CPU, and it also shows us the interaction between the address bus, data bus, and also the control bus. So the control unit requires a memory read, and the result is then placed on the data, and then it will be copied into the MBR and then moved to the IR. Meanwhile, the PC will be incremented by 1, and this is preparatory to the next fetch. And once the fetch cycle is over, then the C will examine the contents of the IR to determine if it contains an operand specifier using indirect addressing. And if so, then indirect cycle is performed. Okay, but for, let's see. Okay, here's the figure. So here's the simple cycle. So the rightmost n bits of the MBR, which contains the address reference, are transferred to the MAR, and the control unit requires a memory read. Okay, you see the arrow, okay, to get the desired address of the operand into the MBR. Okay, what we need to note here is that actually fetch and indirect cycles predictable, and they are simple, but the execute cycle takes many forms, and the form depends on which of the various machine instructions is in the IR. And this cycle may involve transferring data among registers, right, or write from memory or IO, and or the invocation of the ALU. Okay, so like the fetch and indirect cycles, then the interrupt cycle is simple and predictable. The current contents of the PC, I want you to see this is interrupt cycle, must be saved first, so that the processor can resume normal activity after doing the interrupt. Okay, thus the contents of the PC are transferred to MBR to be written into memory. Okay, and the special memory location reserved for this purpose is loaded into the MAR from the control unit. Okay, and in my, for example, be a stack pointer, and the PC is loaded with the address of the interrupt routine. And as a result, the next instruction cycle will begin by fetching the appropriate instruction. So it will make use of stack pointer. This is also very important component. Okay. So yeah, I think this is for the video today. Here's a little quote for you. So Benjamin Franklin once said, "He that can have patience can have what he will." That's all for today. And that's all our lesson for today. Thanks for watching. And here's your to-do list. So please subscribe, give a like, comment, and share this video to your friend. I'll be back on every Monday on the same class in computer science. And don't forget to visit our website at https colon/science.xyz.unux.com. Keep watching and be thoughtful. Goodbye. See you on the next episode.